Welcome all. This is the lecture 6, session 1 of Artificial Intelligence course. First of all, I welcome all of you. Plus, can anybody please confirm that am I audible? Okay. I am getting some messages from your side, but nobody is telling that I am audible. Please confirm this. If anybody please confirm. Can anybody please confirm? Am I audible? Am I audible? Okay, thank you very much. I got the responses. And okay. So welcome to this session. It is a lecture 6, session 1. In today's class, we are going to see some extended version of the search algorithm that we were actually seeing from the last 2 classes. And this is a very important framework in which the artificial intelligence algorithm goes. Okay. So actually in previous classes, we were talking about the systematic search algorithm. They try to search in a particular way where there is some system of the ways are defined, but there are some other ways where you cannot define a systematic way. So we would be seeing some of the algorithms over here. And one more important aspect of the previous algorithm was that everything was observable and deterministic. So hope you understand these terms, that what is meaning by the observable. Observable means that you know that what are the states. And by some means you can get the understanding that what all the states are. So if you are seeing all the states, then your system is observable. Your system is deterministic if it is not changing. For example, if it is a automatic driver car, automatic driverless car, automatic driving car, then the environment is not deterministic. Why not deterministic? Because lot of cars are around and they are also moving. Those things are not static. And can you give me an example of the static thing? Okay, where the things are static. So let's assume that a robot is inside a room and I fix that these are the places where there is some obstacle. I ask the question that how to move the robot from position A to position B. So now the things are deterministic. They are not changing. Okay, observable. He can see. Non-observable when the things are not seen. For example, here also into the automatic driverless car, here also you see that some of the things are not observable, because when you are seeing outside into the front side, you are not fully aware that what is happening at some side locations. Okay, you may be seeing that what is happening backward, but maybe in between there would be something that you are not able to see. Okay, so in many problems, sometimes we are in a situation when we just want to find out what is the goal. And into the previous examples, we have seen that whenever I am going to find out a solution, the path is also important. For example, when we were talking about the 8 puzzle problem, where we had a 3x3 grid and there was some place that was vacant, and you can slide the numbers over there. In the last class we were talking about this. So if you change those things, so you go from one configuration to the another configuration. Okay, you go from one configuration to another, and at the end you go to the reach of the final state, that is actually 1 2 3 4 are all arranged. 1 2 3 4 5 6 7 8, all the things are arranged, and initially the state is given to you, that is actually things are not arranged. So here goal is not important. Although goal is important, but the point is key, what is the goal is not the question, because you know that what the goal is. But sometimes you don't know, but what you don't know that how to reach from this state to the goal state. So therefore the solution means answer would be that you do these movements, you slide this number into the left, this number to the right, and therefore this particular answer is important. But there are some questions where it is not important that how you have reached to the answer, but actually you are actually discovering what the answer itself, goal itself, because goal is not known. So here in the previous case, goal was known, but in some cases the goal may not be known. Such as this example, 8 queens example. You remember the 8 queen example? Do you remember the 8 queen example? It's a chessboard where you have to put 8 queens in such a way so that none of them are actually attacking to each other. So actually the solution is interesting, that how I get this particular solution. It is not important that when you put the first queen, what was the location, when you put the second queen, what is the location. That is not important. In whatever order you add the queens, but at the end I want to see that what is the final thing. Similarly, the second problem, you can see the integrated circuit design. So here I see some components are given to you, and you have to fit this on the integrated circuit. What is the important thing that you want to do? That you have to minimize the cost of the circuit, because if circuit is large, there would be latencies. So you want to minimize the circuit latencies. So I want to the final output. That what is the output? Because earlier when I'm going to specify you the problem, at that time I would not be able to know that what is the answer. Now, this is your responsibility to give me the answer, and I'm not interested that for while designing the answer what you have followed out. Similarly, the factory floor layout, lot of components are there. You want to fit the components into the factory. Job scheduling, automatic programming. The computer should be able to write the program by itself. So I just want to specify the problem and want to see that what is the output. Telecommunication network optimizations, because you want to deploy the minimum number of towers, and so that the maximum coverage is there, sufficient coverage is there. So telecommunication network optimization, vehicle routing. Okay, what is the meaning of vehicle routing? You want to find out the path from place 1 to place B. Okay, and in this also look, try to see it is a very interesting problem that sometimes you may be confused by seeing this problem, because the root, you may be thinking that finding out the solution, the root is important. No, root is not important. Why the root is not important? Because how you discovered the solution is not important. The important is the solution. Whenever we are into this situation when the solution is important, not the way of discovering it, then we go to these kind of systems. Portfolio management. Lot of shares you have, you want to manage them, that how to which is the right kind of portfolio you should go ahead with. Okay, so in these scenarios when the path is irrelevant and the goal is only important, okay, then we go for the local search algorithm. Okay, most of the time we go for the local search algorithm. So today we are going to see some local search algorithms that are very important, and we are also going to see what are their properties. Okay, and the one of the important property of these algorithms is because they are localized, so in their locality they want to find out the right solution, and when that solution is actually, if they find out the right solution, their state changes, and into the new state again they apply the similar kind of framework to find out the next solution, and similarly one by one they find out the solution from place A to B, B to C, etc. Is it clear? Do you have any questions? Please, you can ask. Please, please ask. Is it clear? Okay. So if you apply the local search algorithm, the most important thing is this, that these algorithm uses very little amount of memory. Okay, and they can find out the solution very effectively. Even sometime it is even if sometime you have the infinite state space, because sometimes if the state space is infinite, just see that, let's assume that a space, if state space is infinite, means all the possible states are infinite. Even if if you see what is the number of states into chess game, so it is also a very big number, because it is also going to be a very big number. All the possible board positions, so it is going to be a very big number. So in those scenarios also, sometimes these things can give you a very large solution, very reasonable solution. So can you tell me one thing? I have a question for you, that in case you want to solve the 8 queens problem, okay, you want to solve which problem? 8 queens problem. So how many states are there? Means, can you tell me that in the state space how many states are there? Can you give me the answer? Can it be right? I'm waiting for you. Okay. 8 queens problem. What is the 8 queens problem? That you have a chessboard, and in that chessboard you actually want to put 8 queens. How many queens? 8 queens you want to put. And can you tell me that how many different state space are possible? How many states are possible? Okay, one thing we can assume that we are not going. If we assume that we are not going to put the queen into the same row, sometimes it may be possible that you can put it there, but let's assume that in every a very general way of understanding this, that you would be putting one queen into this row, one queen into this row. Every row would, sorry, every column would have only one queen. Why? Because if you are putting two columns into the room, the queen attack each other, and this we don't want. So how many ways you can put the queen over here? 8 ways. Okay, you can put the queen over here or here, 8 ways you can put. And in every possibility, you can put the queen here, also. Here also, you can put 8 queens. And for every combination of these two, you can also put 8 places, the second, third one, and similarly 4th one, similarly 5th one, 6th one, 7th one, and 8th one. It comes out to be 8 to the power 8. How many of them? Can anybody tell? Okay. So can anybody find out what is the 8 to the power 8 is the value? Okay, so it's not that difficult to find out. Just see. Well, let's ask from Google that what is the value. Let me just ask that what is 8 to the power 8. See, 8 to the power this number. This many number of states are there. It's not very less, but okay. Also, it's not very big. It's manageable. So you understood that what is the state space, how many states are there, and how many of them have the solution. This is another question. So local search algorithms, actually the one thing that I want to tell you, that the local search algorithm, they can solve many of the time a kind of the problem that are related to the optimization problem. So what is optimization problem? Is given something, given some condition, you want to find out the solution that fits your parameter the best. Okay. Are you there? One minute. So okay, I wanted to tell this particular thing that sometime if you are only interested into the solution, so you can tell that give me the best solution, give me the optimal solution. This is the important part, okay? Because I would specify the problem and then I would ask that give me the optimal solution, such as say I can give you the set of linear equations and I can ask that what is the minimum value, what is the maximum value. These are the optimal functions that I can ask. And then your task would be to give me the state in which that particular function gives you the optimal value. So here, this is an important diagram that we call the state space landscape diagram. So what does it mean? That look, whenever we want to go for these kind of solution, when only the final state is important, we have a function that is called the objective function. Okay. So objective function is a very different kind of function, very important kind of function that gives you the point values. Means if you specify all the values on that point, you are able to see that particular function. So look, what is difficult? If you know that all these are the parameters, if you know that these are the parameters, if you know that this is the function, then what is the right way that you can very easily find out now? What is difficult? Why it is difficult? I give you the function, and I ask that on what particular value of x this function is going to give me the maximum or minimum. Why this question is difficult? This question is difficult because what should you use as an increment of the decrement of the value? Okay, what should you use for the increment and decrement of the value? If you are going to choose the incremental decrement into the x to be very small, then you essentially are going to take infinite time. Let me just tell you why. So can you tell me in the real number how many numbers are there? In real number, in set of real number, how many numbers are there? They are infinite number. But if I ask you that I'm going to find out how many numbers are there between 1 and 2. So you know the distance is not very large. Distance is only 1 between 2 and 1. But how many numbers are there? So they are infinite number. Okay, there is a proof for that. We are not going to much detail into that, but if you are interested, you can find out very easily on the internet that there are infinite many number between any two given number. So even if I ask you that for how many numbers are there between 1 and 0 and 1.1, now even I have the smaller area, but there also there are infinite number of items. So therefore, for testing for each of the items for a continuous domain is not a good idea. Going to be very difficult. So just see this. This is a kind of illustration that let's assume on the X space you are putting all the state space in some increasing order, and this is the objective function that gives you the value. So look, a very typical kind of function it is given. Very difficult to come up with this kind of function, but let's assume that you have a function, and then you can analyze some of the things that here. If you are coming over here. Go here and just tell you this thing that if you are here, okay, what is the value? This is the value. If you are here, what is the value? Here. What if you are here? What is the value? This. What is here? What is the value? This. Here. What is the value? This. So if I ask you that in this range I want to find out what is the value of x on which this particular function gives me the maximum value. So you know that since maximum value is this, so you see that what is the projection, and you see, and this is the answer. Okay, this is the answer. You say that this value actually represents the global maximum. Okay, so this is the one thing, and in this graph there are some very important things that you should also consider, that this particular point is actually maximum for this particular range. If I say that my range, my domain is this. My domain of this item, I'm going to only consider these kind of these items only, then the maximum is this. But if I increase my area, then the maximum becomes different. If I increase my area, I say that I want to find out the maximum item between this range, then this is no more the maximum element is this. So and with respect to this place, you can say that this is the local maxima, because item is at local maxima when it is high, this value is higher than the nearby values. But global maximum has actually the highest value. There are two important other points also. This is a flat part that is called plateau, because here it is actually at the maximum, and all other and here at this place all the values are same. So this is a problematic area. Okay, the algorithm, whenever it comes over here, you don't know that where to proceed. Because if you are here, you can see two values nearby, and since you find out that here at the second point the value is higher, so you shift your x. Okay, what I mean by this is actually we are going to study very recently. Let's assume that randomly you want to find out the global maximum. Okay, let's assume that you want to find out the local maximum. So you randomly start. You have randomly started at this particular point. Okay. At this particular point. So what is this point? This is the point. Okay. At this point, what is the value of f? So you see that this is the value of f. This is the value of, what is the value? Let's see, it is 10. Let's say that it is 10. Then what you do that you take two nearby position, because it's only one dimension. So there would be 2 points which are nearby. So you see what is the value over here. So you see, can you tell me what is the value? If it is 10, then this value is going to be less than 10 because it is smaller. Okay, so this is the value. At this point, at this point x, the value was this much. I am telling that it is 10. At this particular point where x plus I am talking about, the value is going to be this. That is going to be less, say 9. At the third point, let's assume that I take another point, that is x minus. At this point, if I want to find out what is the value, I see that this is a value which is bigger value, so I can say 19. Okay, so whenever you are at this particular point x, you see the nearby points, 2 nearby points, and you can evaluate the function, and then you observe that okay, on the x minus the value is larger, and since you want to find out the global maximum, therefore you should shift towards the x minus. You should shift towards the x minus. So now x becomes this value. X becomes this value, and the same thing you apply over here also. you again find out that what is the nearby thing. So you would be seeing that this particular point is going to have the higher value. You keep shifting into this way, and then at some point you would be able to reach the global maximum point. And at that point you would be able to see that okay, no nearby point is going to give you any different value because higher value. So you would stop at this moment and you would give that this as a solution. Okay, so this is how you go to find out the local maximum. Okay, so this is actually we want to study. So you understand this thing. Okay, any more question? So if you just want to get an idea, this particular thing has been published from a very recent paper that real estate space landscape means sometime see that this is a two-dimensional landscape. So if you are here, just see that if you are here at this particular point, and so global minimum is here. So if you want to go to this particular point, so you see that all over around how to reach over that point. There is no path, doesn't look any good path over there. What would happen that from here you would go and you would reach at this particular point and you would say that okay, I'm at the top. Okay, if let's assume that you want to go to the top, then the top is here. How would you reach to this particular top? Very difficult. If you want to go to the minimum, how would you reach to this particular point? Okay, if you start from this point, then it is very easy though, because things are very easy. But if you start from here, then going till here is going to be difficult part. This is what is you should keep in mind when discussing the next slides. This is a very important part. Okay. So one such algorithm is called the hill climbing search. And one such approach is the hill climbing search, and we have just discussed some of the idea over there. That is steepest ascent version. Okay, we are going to see the steepest ascent version. It tells that if all these, what are the points? What is the state space? This is the point that you see from the satellite. Some of the points you are going to see. Okay, so from the satellite, the things would be flat. Okay, it looks like a flat. But when you are going to evaluate that what is my height, then only you would be able to see that there is some height. Understand, na? If I want to print the things on let's assume that from the sky you take the picture, everything would be flat. But if you want to evaluate that what is the altitude of this particular point, then only you can see. So steepest ascent means look around and choose the best. It's a greedy local search, and it makes a quite rapid progress. How it does? The same thing I told you that on this landscape, what you do on the landscape, what you are going to do. So let's assume that this is a hilly area. And instead of hilly area, you have taken the image from the top, from the satellite. Then everything looks flat. So what is going to happen that if you want to measure out these points, so what is the value altitude, and then you also evaluate what is around. You randomly start how you can reach to this particular point. If you want to reach, let's say you want to reach to this particular point. How you can reach, because on this image there would be various points. You don't know what is the point where the maximum altitude is there. So what you do, you start from any random location. The algorithm is this, that you start from any random location. Let's assume I start from here. Okay, let's assume you start from here, and then you evaluate that what is around you. All these points you evaluate. Okay, all these points you evaluate. So and find out that what is their altitude. If this altitude is say 100 meter, and some would be having altitude 90, some 95, some 105, and some so on. So what you should do? You should from this point you should shift to this point. Okay, 105 point, and then you again apply the same algorithm over here. So to again apply the same algorithm means then you are evaluating the nearby point over here. And you are seeing that what are the values. So somewhere you see that there is a value 108, some 90, somewhere 80. So you would proceed towards 108. Correct. So let us see this algorithm. Same thing is written into the algorithmic form, hill climbing algorithm, where you are actually providing the problem you are going to provide. And it is trying to find out what is the initial state. Okay, just find out what is my initial state, and sometimes if there is no other way, so you are taking a random location for a starting point. Okay, and then infinitely many times it is going to apply a while loop over here, a while loop until it terminates. So algorithm would automatically terminate if when it would find a solution. Otherwise, what it is going to do? Highest value successor of the current. It is going to find out. This is an important function. Highest value successor of the current. What does it mean? What is the current? Current is this. Okay, I am telling the current is this point. Okay, current is this point. What is the successor? Successor are these things which are nearby, because you are standing over there. They are your successor because you can go into any direction. Then you are evaluating them, finding out on what point it is maximum. So you see that out of these things, this point has a maximum. Okay, so if you find out this as a maximum, then you compare that whether this particular whatever big neighbor has the value should be, if it is less than your current value, means because you are seeing highest value, so highest value out of them is this, and with that is less than you, it means that you cannot go over here because all your neighbors are smaller than you. If all your neighbors are smaller than you, then you are at the peak. So then you are actually returning the current state because it's your answer. Otherwise means if you find out something that has a higher value than you, if this value is 100 and this value is 105, okay, then what you are going to do? You are going to shift on this. You are telling current is equal to is my neighbor is becoming my current. So this is the way you forward. You go forward and you can find out the solution. Okay, so let's see an example into the hill climbing search. You have seen. Let's apply the hill climbing search into the 8 queen problem. You know the 8 queen problem. This is the place. Means the chessboard is there. You want to put 8 number of queens. So you want to put, as I told you, that you want to put one queen in one column so that they are not attacking. Okay. So successor of a state means, let's assume that you are into this state. How can you find out the successor? Successor of the state are all possible states generated by moving a single queen to another square. Means sometimes this is the thing. So what you can do? Okay, if this is the state, what you can do? What are the possibilities you have? Let me tell you. The possibility is this, that you take this queen. Okay, you take this queen and you put it here. This is one possibility. Okay, but if you do it, you are going to have something. It is written as 16. What is 16? Actually, this is a heuristic function. Let's first understand that what is the heuristic function, because you want whenever you have some board position, you want to assign it as a how good it is. Okay, you want to assign it a how good it is. So to define this, you develop a heuristic function, and you know what is the meaning of heuristic function. It try to give you estimate that how much it would take to reach to the final answer. The heuristic cost function is the number of pairs of queens. Number of pairs means how many two different queens that are attacking each other. Okay, so in this particular location, in this particular board arrangement, there are 17 such pairs. Can you find out any of them? Can you find out any of them? Look, this is being attacked by this. This is also being attacked by this. This is also attacking on this. Okay, for this it is 3 attacks. Okay, for this again the same pair you are not going to take, but this is attacking on this. This is attacking on this, and similarly this is attacking on this, and this is attacking on this. This is attacking on this. This is already you can find out how many attacks are possible. So there are 17 such attacks. So I give you the this particular problem that try to find out that how many attacks are, how many queens are attacking on each other. So the point is that there are at this particular moment there are 17. There are 17 such. There are 17 pairs of queens that are attacking on each other. Okay. So this particular thing says that if what I can do, I can take this to this particular location. If I put this, then what would happen? This particular number tells that now 14 would be attacking to each other. So you understand now what this number means? Means if you are moving this particular say this particular queen, if you move this to this particular location, so now 14 would be attacking each other. If you put this queen, if you put this particular, let's assume that this particular queen at this particular location, so 17 would be attacking. Okay, and you see that everywhere sometimes it could be bad also. For example, if you now you are at a 17, but if you put this particular queen at this location, okay, so what is going to happen? 18 pairs would be attacking each other. You would not like to go on that situation. You would like to go that from 17 I should find out a move so that I should this number is reduced, so that number of attacks should be reduced. So you see how many such places are there. Okay, you see that there are some places. What are the places? This is the place. Here if you move anything, it is going to be 12. So this is the best that you can do. Okay, in this scenario, this is the best you can do. So there are various best available. So which one to choose? That's again a big question. But if it has been only one, then you have chosen anyone. But let's assume that randomly you choose anyone. You put this thing over here. This is the next state. Then what would you do? You would again try to find out the same all the numbers, and then you would move somewhere so that this number from 12, because you have seen that you have reduced from 17 to 12. Now you want to remove, go ahead to 9, then you want to go ahead for 5, and so on. At the end, if it is 0, then you are done. So this is the board arrangement. Somehow if you go from 5 to 1, so this is one such arrangement. Here h is equal to 1 only. Okay. So I think who are the two who are attacking? I think these two are the attacking. No other else are attacking. Okay. So this is a better solution. Okay. So from here you can reach over this particular place. Correct? Okay. So we have find out this, that you need to understand from this slide only one thing, that if some state is given to you, then you see that what are the possibilities that you can do. So how many possibilities are there? You can move this at all these positions, and then in all those positions you are going to find out what is the value, what is the h value. Okay, heuristic cost function. What is the heuristic cost function? Similarly, you can move this. Because into the one go you can only move one queen, because one queen can jump from here to here also. You see all the places where it is possible, and then you see what is the minimum number. Those are your candidate to go into the next. So similarly, you can go from one place to another and find out the solution. But there is some problem. Okay, this particular algorithm gets stuck. Sometimes algorithm reaches to a state where no further progress could be made, because now there is no possibility that you can improve. This could happen because of the two reasons. One is the local maxima, okay, ridges and plateaus. Okay. So what does it mean? Let me just tell you what is going to happen. Okay, there could be local maxima, ridges and plateaus. So I told you that. Let me just tell you once again that what these things are. So let's assume that the function is going to into this way. Okay, and as I told you, because you are starting from any location, so random location. If you start from this location, what is going to happen? This algorithm will bring you to this point, and from this point you cannot go ahead, because all the things which are nearby, they are actually smaller than you, so you cannot make the progress. So this is what the problem of local maxima or local minima. Similarly, you can see the minimum also, because if you want to convert this problem to the minima problem, you just find out what is the sufficiently large number, or you multiply everything with the -1. So things would be just replaced, things would be just reversed, and you can solve the same thing. Okay, so you find out what is the local maxima, problem, because sometimes if you are starting over here, so you would be making the progress in such a way so that you are stuck over there. Similarly, you can see that if you start here also, again same thing would happen. Okay, if you start here also, same thing would happen, because you are going to reach eventually, you would be actually there. Then next thing is the recess. So what is recess? That recess is actually, sometimes you can find out these kind of things. Okay, they are ups and downs, but they are kind of this thing. So they are not all the values are nearly same, and they are going up and down, up and down. So everywhere from here you are stuck over here, then you cannot move. So these are also similar kind of local maxima kind of problem, because it's again the problem, but the problem is severe because here only one peak was there, but here lot of peaks are around. So you are having big trouble. Another problem could be that if I say that at this particular location, if I put this particular thing, that this is the thing. If this is the shoulder or plateau, then you are again into the problem. And what is the problem? That if you start from this particular point, you would be moving here, 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 and here. But from this point, you would not be able to move, because everything nearby you have the same value. Then you cannot go anywhere. Then you are again stuck, because your algorithm was such that if the value is larger, then only you are moving. So this algorithm cannot move. So again you have a big problem. Okay, so this is an issue, that you started from some value. You want to solve this particular problem, 8 queen problem. You started with the random board position, and then you have find out that what is the H value for all these position in the next move. Because if one move you find out all these value, you find out, okay, I have a value, then you go to the 12, then from the 12 you can go somewhere else. But here, for example, if you reach over here, now you cannot find out any progress, because you cannot make it 0. Okay, so there's some statistics that is starting from the randomly generated 8 queen state. Hill climbing gets stuck 86% of the time. Mean only 4% of the 14% of the problems are cases you are going to get the solution, or 86% of the time you are actually stuck. Okay, and it takes only 4 steps when it succeeds. Just think how good this algorithm is. How many states we had? I think we have computed over here. How many states we had? We had I think this much, 1 crore 67 lakhs states we had. Okay, this much number of states we had. So it is not going to evaluate all those things. It is very quickly going to reach to the solution, and that is very quickly going to reach the solution. Only into the 4 steps it is going to give you the solution. Are you able to see this? And when it fails, means it only takes 3 steps and then it stops, because now it is not, it cannot all the nearby places have higher values, so it cannot go forward. If all the nearby places have the more higher value of H, it cannot go forward. So in 3 steps it actually gets trapped when it is failed. Okay, so it's a quite impressive algorithm, but the point is that most of the time it is going to stuck into the into this local minima problem. Okay, so what is the right way? So how can you come up? Because it may be possible that nearby places all have the same thing. So you can allow the sideway moves in this scenario, because you are seeing that you cannot improve, but you can see that the values are same. So you can allow that, okay, if the values are same, you can go to the other values. Sideway means move means you can go right hand side, or you can go left hand side, or you can maintain the direction whatever your direction was, because you can find out the earlier when you came into the scenario what was your original direction. Then you can go into the same direction until something. But then becomes a problem. What is the problem? That how many sideway moves you can take? It may be possible that you can take infinite side moves. And if you are stuck, then you are again stuck, because it may be possible stuck, and it can go forever, and it is not going to give the solution, and even your algorithm is progressing, but executing and taking time, but you are not going to get the solution. Okay, you reach to this particular level, you are taking the right moves, but you are not getting the solution. It may also be possible. So what is the better way? That put a limit on this. Say only 100 times I would move to the sideway. Okay, if you say that I would only move 100 times, okay, if you say that I would move only 100 times to the sideway. What do I mean by this? That I mean this, that let's assume that this is the graph. Okay, so if you say that look, you know that in the successful things it only takes 4 steps, but in the unsuccessful things after 3 steps there is no move. So what happens that let's say you started from here, after 3 moves you are here, and now you didn't find anything useful. So you are saying that I am going to allow that you go ahead into this way, but it may be possible that this distance could be infinitely long, and therefore this particular processing would take infinite amount of time to reach over here. This may take infinite amount of time to reach over here. What is the other way? The other way is this, that you say that okay, whenever you are stuck into a problem, you only explore to the 100 steps. If into the 100 steps, and this is say 100 step, if into the 100 step you don't find a solution, you stop. You say that there I am not able to find. Then what would happen? The algorithm would reinitialize you. So let's say, so definitely algorithm would not initialize you here. It may be possible the algorithm can initialize you here. And when the algorithm is initializing over here, then into next 4 steps you would be able to reach over here. If algorithm initialize you at here, then also you would be into 4 steps would be reach over here. So why you bound yourself in a situation where you are actually there is a possibility of infinite side moves? So the better way, you put a limit on this. You say that after 100 moves, I would say that I would not go ahead. So this algorithm, if fails into the 100 step, fails, otherwise it gives you the solution. So now it solves 94% of problems. If you change this algorithm in this way, that what is the new algorithm? That if there is an improvement, you are going to take the step. If there is no improvement, then also you are going to maintain the same direction until 100 steps. So you may be into 100 steps, you may be reaching somewhere from where you can find out the solution. Otherwise, if you don't find a solution to 100 ways, then you stop. So this is a big thing, and now it solved 94% of the problem. You say that earlier it was only solving 14% of the problem. This is a very good improvement, okay? But it takes now 21 steps to solve on average, and 64 steps for the failure on an average. It is going to take, earlier it was taking only 4 steps. So why it becomes 21, can anybody tell? Okay, because some places where earlier it was a failure, it has actually succeeded, and therefore, and those steps would, how many steps they would have taken? They have taken 3. The earlier failure had taken 3 steps plus something less than 100. Okay, so this many number of steps are actually there. So you find out their summation, because although if all these were randomized earlier and only 14% were earlier through, now we are going to see that for some more are through. So these numbers were actually 4, but these numbers are larger, say 20, say 15, 30, sometime you less than 100. So their summation, if you find out the average, it comes out to be 21. Okay, and similarly for the failure cases, now again the same failure cases are actually 64. So all the failure on the average, they are taking 64 number of steps. Okay, so what is the bit suggestion that how can I come up? One way we understood that in case we are stuck into the place where there is all the values are same, then I would apply the side moves. But but sometimes it may be possible that you are not into this situation, you are onto the peak. Then what would you do? Because it may be possible. There are 2 problems. One problem was this, that you are when you are at this particular location. When you are into this location, then you have applied the sideway move. But when you are into this position, into the second position where I am telling that here some local maximas was there, then if you are stuck at this point, then what you can do? This is another point. Okay, this is another thing. What this is not the same thing that you can apply the sideway move. What would you do into this scenario? Into this second scenario. To go around this, there are a few important methods that you can see. One is a stochastic hill climbing. This is a very novel method that tells that you can utilize the probability values. Okay, you can utilize the probability values. So let me tell you how. Okay, what is stochastic hill climbing? Okay, what is stochastic? What is stochastic hill climbing? Okay, stochastic hill climbing. What it says that just see this example. Very simple example I am going to construct. Let's assume that you are at this point into two-dimensional space. Okay, let's assume you are into two-dimensional space. Let me also say that it's an image. Let's assume that there are only how many places are available. Let's assume that this is only these places are available to you to move. So how many places are available to you? This place, 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 and this place. Okay. Okay. Let me tell you. Let us just assume that this have the value, say 90. Okay. So, and also let's assume that this value 110. This value has 105. This also have 110. This has 80. This has 70. This has 65. This has 90. This has 55. Let's assume these are the values. So what it tells that you should earlier algorithm. Can you tell me where the earlier algorithm would go? Earlier algorithm, where the earlier algorithm would go? Just to remove the confusion, let me make it 112. Okay. So earlier algorithm, in what direction it has gone? It has gone to this direction. Okay, because this value was 112. But this time stochastic hill climbing says that you find out the steepness. What is the steepness into every direction? So since you see going 65 is not a right choice. Going 55 is not a right choice. Going 90 is not a right choice. Going 70 is also not right choice. Going 80 is also not right choice because they are descending. Only 3 ascendant locations you see. That these are the places where you should move. So what you should do, you see that what is the difference? Can you see the difference? The difference is 100. Difference is 22. This here, if you go into this direction, difference is 22. Go into this direction, difference is 15. Okay, if you go into this direction, difference is 100. Difference is 20. The difference is 20. Okay. So you don't earlier it was necessarily that you are going to this particular direction. Now I am going to say that you go to this direction with the probability that is 22. What is the summation of 20? This number and 15. This number and 22. What is the summation? 7, I think. 57. So with 22 upon 57. This is the probability of going into this direction. In this direction, the probability is 15 upon 57. In this direction, the probability is 20 upon 57. So you are moving into these places with these probability. What do I mean? I mean this, that okay. So you are here. You move into this direction with the probability 15 on 57, with the probability 22 upon 57. This direction, what is 20 upon 57. So what is the meaning of probability? Probability makes this particular point that it is not confirmed that in which direction you would go. So you would roll a dice. How would you roll a dice? Okay. So you would roll a dice in this way. Let's assume that you have you have a 57 meter tape. On this tape, up to 22 meter, for every 52, let's assume you take 52 centimeter of tape. On the first 22 meter, everywhere you write, say this is the right move, this is the left move, and this is the down move. At 22 places you put right. You put R. Okay, let's put R. You cut it, all these things. How many chits you have with the R? 22. Similarly, you take 15 chits. How many? 15 chits. Written D. You take 20 chits. Written 20 chits. Written L. 22 chits. Written R. You have taken how many? This probability means that you have taken R, D, and L. You have made chit. How many chit? 22 chit. And with the down 15 chits you have, with this 20 chits. And now you put them into the basket. You shuffle them and you pick one of them. So can you tell me what is the most likely direction you are going to go? This is again the 22.57. Therefore, the probability of going right side is higher. But you can go to the any direction. Out of these three directions, you can go any direction because you are actually using the probability to go over there. So I have given you the framework also, that if you want to implement this, what framework should be there. This is a kind of framework that you can use. You put all the small chits over there, and out you draw from that. Whatever coin you get, whatever page you get, whatever coupon you get, based on that you go into the left, right, and down. So this is how you move. If you move in this way, it is a stochastic hill climbing. Understand this thing? Can anybody say yes? Do you understand this stochastic hill climbing? That you are actually defining that what is the steepness, and that steepness you are going to use for the probability to going into that particular direction. This algorithm also converges, but its convergence is something slow. Okay. Next algorithm, that first choice hill climbing. First choice hill climbing. This is an important thing. Do not explore the state space when you see the first improvement. Means you are here, you are nearby, seeing that what are things which have the higher value. Whatever the first value you see that it is greater than me, you go and into that way. Means you are not finding the best one. Around yourself, you are not finding the best one. You are only around yourself, just seeing the one place that is better than you, and you are moving in that direction. What is the advantage? Sometimes if you take the wrong decision, that is also perfectly fine, because you see that this is the scenario. Okay, this is the scenario. Just see how difficult it is to get around, because if you are here, going from here to here, it is lot of problems you have. You just see that it's not that easy that you are going into one direction. If you are going to this direction, then again there will be no new mountain that would become a problem for you. So you sometimes take right decision, wrong decision, and then ultimately you would be reaching to the right place. So this is the first choice hill climbing. It tells that whatever place you are there, you explore nearby places. The first place that you find out better than you move to that particular thing. The stochastic was difficult, no? For the stochastic, you find out what all the things are around. Then you find out what is the steepness, and then based on that steepness, you assign the probability, and then you choose a right appropriate path. Next is a very important and very lucrative kind of approach that tells that the random reset hill climbing. Okay, random reset hill climbing, and that the idea is fairly simple. And the idea is this: that it tells that can you give me the answer of a very simple question for me? Okay, and my question is this: that okay, my question is this, very simple question, that let's assume that you have a coin, okay, and the probability of head is 0.3. Okay, it's not 0.5. Okay, if I flip it 10 times, how many heads you are expecting? Can you tell me? If I flip it 10 times, how many head you are expecting? Please tell me. Anybody, please tell me. if I have a coin whose probability of getting hit is 0.3, I am flipping this 10 times 3. Correct. Very good answer. 3 times I am expecting. Okay. I am expecting 3. I am flipping is 100 times. How many? 30. Okay. This is what the answer is. That is very straightforward. Okay. So if I want to find out one head, at least how many times I should flip this? Can you see this? It comes, if I want to find out number of head 1, how many times I should have flipped it? It is 10 by 3. Is it right? Are you with me? 10 by 3 times. What is 10 by 3? 0.3 is 3 by 10. 0.3 is 3 by 10. And this number is actually 10 by 3. That is the reverse of the previous number. If the probability of success is P, then run the 1 upon P number of times. Then run the algorithm 1 upon P number of times. Definitely you are going to get a success. This is what the point is. Previous setting we have seen that if we start randomly 8 queens problem, then it is going to 86% time it was failing. Okay. So 14% time it is going to give you the right answer. I mean the probability of success was 0.14. Okay. Are you with me? If this earlier we have talked about that in 8 queen, if you apply this the hill climbing, 14% time you would be able to get the solution, otherwise you would be stuck. The probability of getting solution is 0.14. So if you run this 1 upon 0.14 number time, that is nearly 7. If you run this algorithm 7 number of time, then one of them is expected to get you the result. It's simple. It's very simple. Okay. So if you run 7 number of time, so what you expect? That 6 times you are not going to get the solution and 1 time you are going to get the solution. When you are not going to get the solution, you are stuck in that step. In that things you are spending 3 steps. So 18 number of steps you have to spend over here, and every time you are stuck. You may be lucky that into the first try itself you got this thing 1. But when you are getting the solution, you are giving the 4 steps. Total number of steps is 22. So out of 22 number of steps, you would be able to find out the solution. Do you understand this? Any questions? Kishore, are you with me? Okay. So I'm going to close this session over here. Then I think we are done with this. So I'm stopping this.